Thank you. Yeah, I got to distribute that 16 to all three of them. Okay, so there's a couple things that are going to happen now algebraically. If you look at this thing, what's the first thing that's going to happen? Yeah, those 64s can cancel. And now look at it. If those 64s are gone, you're just left with this in the middle, right? There's something else that can happen then. You can factor, and then after factoring even, what can you do? Yeah. This 16 right here? This? From the equation. It's 16t squared. So I did 16t squared. Because our t was 2 plus h. So what's going to happen in that middle there? Yeah, we can factor that, but more than that, though, yeah, that h can go away now. We can cancel that out. So if the h's are gone, and these 64s are gone, we've got the limit as h goes to 0 of 64 plus 16h. Okay, that's doing both those cancellations there. So take a look at what we have now. Remember before we wanted h to be 0, right? We said if h is 0, then we've got what we want. That's the instantaneous rate of change, right? And we couldn't do it up to this point because we'd divide by h, and that's bad. Or we divide by 0, and that's bad. But now that we've canceled the h using our algebra, we got something we can use, right? Plug in the 0. What's the instantaneous rate of change here? It's 64. That's the answer. It's not an approximation. That's exactly what it is at 2 seconds. 64. Okay, so we are capable of figuring out how quickly something is moving at an instant by using this rate of change idea. Okay, this is what we just did right here is called the difference quotient. You might hear that lingo later on, but that's what this is called when we do this instantaneous work like we just did here with the h's. It's a difference quotient, but it allows us. Because every single time you do one of these, you should end up in a spot where the h will cancel, and then you can plug in, and then you've got an answer. Okay, so this allows us to get at instantaneous rates of change. And later on, we're going to look at derivatives, and what derivatives do is streamlines this process for you. So you don't have to sit here and write out all these limits every single time and go through all of that gobbledygook to get to the answer. You can just do like a two-step boom, boom, got it type of a thing. But that's essentially what a derivative measures, though. A derivative is an instantaneous rate of change measurement. Okay, that's its definition. So we're going to get to that later. But for right now in Chapter 2, like I said, we're going to focus on the limit stuff and work with that a little bit more. So I really wish I could have you guys practice this a little bit more, but I got to move on. So, but we will get some time to practice that a little bit more later. So since we need to use limits to do these calculations, we had that limit as h goes to 0 part of that thing that was how we got through that. It's worthwhile to just talk about limits in general here for the rest of the time. Make sure that we're okay with how we do those types of calculations. So we're going to jot down a few things that we know about limits, and then work on a few practice problems involving them. So what a limit is, so it is a value that a function approaches as x approaches a value. Okay, so when I say a value that the function approaches, what kind of value is this? Well, it's a y value. So what happens to y as x approaches something else. Okay? And some of the easier ones to look at are if you have a graph in front of you. So that's what we're going to do first. We're going to take a look at doing limits on a graph. So let's start with that graph. See if you can answer some limit questions for me. So what is the limit of f of x as x approaches infinity? What is the y value that it's getting closer and closer to as x goes to infinity? What was it? 0, yeah. Okay. Now we're going to talk a little bit about these guys some more later, but I might as well talk about it now that since we got one in front of us we can use it for. I'm going to zoom in on this a little bit for you. This next one, see I put that little negative up there by the 0, kind of like an exponent? That means from the left. Okay, so what is the limit of f of x as x approaches 0 from the left side? Where's it going? To infinity. Yep. And then likewise, what is the limit as x approaches 0 from the right? So I put a little plus sign up on that 0 there, and that means from the right side. Yep. Negative infinity. Okay. So that's kind of the idea looking at a graph. Now, they might give you some other ones that are like so easy they're hard or so hard they're easy. I don't know. Where it seems more difficult than it actually is. But maybe not. I don't know. So let's say we've got a piecewise defined function here that looks something kind of like that. Let's see, this is at 1, this is at 2, this is at 3, 1, 2. Okay, so something kind of like that. And I'm going to do the same thing. I'm going to ask you some limit questions next to that one and see if you guys can answer them for me. So what is the limit of f of x as x approaches 1? So as x gets closer and closer to 1, what does the value of y get closer and closer to? 0. Nope. 3. I think maybe you did -1. But as we get closer to an x value of 1, or maybe you're doing this one instead, yeah. As we get closer to an x value of 1, where's the y value? Up at 3, right? So this is equal to 3. Okay, so what is the limit as x approaches -1 of that function then? So as x gets closer to -1, y is getting closer to what? That one's 0. Mm-hmm. Okay, what about that one? What's the limit as x approaches 0 of f of x? From the left, it's 1. What if I went from the right? That one, well, it doesn't actually get to 2, but it approaches it, right? So this particular one, if I had made this like a little from the left with the negative on it, then the answer would be 1. And if I made it from the right with a little plus next to it, that answer would be 2. So what do I do with this then? What is the limit as x approaches 0 then? Well, it doesn't exist. Because it depends on which side I'm coming from, right? All the rest of these, the limits from either side approach the same thing. Like for 1, it doesn't matter which way I approach it, right? Both of them are coming up to 3. -1, doesn't matter which direction I approach it from, both of them are coming together at 0. But this one, as I approach 0 from either side, I'm going to 2 different places. And that limit can't exist then if it's coming from 2 different places. So we would just write DNE, does not exist for that one. Now, like I said, though, that being said, if I had done, like, let's say the limit as x approaches 0, let's go from the right. It's called a right-hand limit. So what is the answer to that one then? Like I said before. Approaching 0 from the right, it's 2. Yeah, it's approaching 2. So that still exists. It's just the limit by itself approaching 0 can't exist, though, because you can't have 2 values for the same thing, for the same limit. Okay. So even if there is a hole in a function, there's a space missing or something like that, the limit still exists, but the value of the function does not. And this is something that a lot of students in the past have struggled with a little bit. So I want to make sure that I kind of hit it a little harder this time. So let's say we've got this function. It's got a removable discontinuity in the middle of it. It's like somebody just shot a hole in it. And it's defined for every x except for, let's say, 1. And this is 1 up there as well. And let's make this a 2. Sorry. Using 2 different numbers will be easier to see what's going on. So let's say that's 2. Okay. So the limit of this function as x approaches 2 is what? It does, actually. It would be 1. Now, if I asked you what is f of 2, what's that? What's the value of x, or what's the value of y if I plug in a 2? Well, there's nothing there, right? So does this have an answer? No. Does not exist. Can't do it. Undefined, however you want to say it. Okay, the limit exists, but the value of the function there doesn't. Okay, because a limit measures what are you approaching, not what is it exactly at that spot. Okay, and that's an important distinction between these two things. Okay, so think about it. I always talked about approaching from either side. Okay, the limit as x approaches 2. So as I approach 2 from either side of this thing, what value am I approaching? 1. Am I ever really getting there? No. But am I approaching it? Yes. So the limit does exist. The limit is equal to 1. The value